Hi, my name is Skylar Moe, and today I will be presenting Lab 3, Black Hole Motion Forces for Physics 2211. So our problem here is to find the mass of a black hole. We will calculate the mass of a black hole using data from its interaction with the orbiting star using Python, GlowScript, and Georgia Tech email address as a seed to formulate the star trajectory around the black hole. With our data, we will calculate the net gravitational force of the black hole on the star. Use Fnet, mass of the star, and the position of the star, where r represents the position in our final calculations. We'll continue to apply Newton's fundamental laws, the momentum principle, third and first laws in the entirety of the lab. These are our initial conditions. We have the system, which is the star. The seed is skylar.mo@godtech.edu. The mass of the star is 2 times 10 to the 30 kilograms. For our constants, we have the mass of the black hole and the mass of the star. As we can see, our mass of the black hole is not necessarily constant, and our surroundings is the black hole. Note that no other gravitational interactions will be present. So here's the GlowScript code, which is essentially just setting up our initial conditions. So we have G, which is Newton's universal gravitational constant, the mass of the star, and delta T, which is represented by the amount of seconds in a day. In this part of the code, we can apply our basic definition of momentum and change in momentum. Then on lines 177 and 179, we have Newton's second law, which is Fnet is equal to dp dt. We calculate dp dt by doing delta p over delta t. These lines allow us to break Fnet into its parallel component, which is then used to find the perpendicular component later in the code, as we see Fnet parallel equals dp dt parallel, and then dp dt perpendicular is equal to dp dt minus dp dt parallel until our Fnet perpendicular just equals dp dt perpendicular. So here we have our data visualization, which we will use arrows, and we set the arrow scale to 1 times 10 to the negative 17, which is approximately 1/3 of the mass of our star of the black hole. So here's a model. As we see, when the star gets closer to the black hole, the arrows grow larger, which is indicative of Newton's universal law of gravitation because it is an inverse square law. These are the results after running the computer simulation. The simulation produces a series of different mass values. The black hole mass was not constant, which can be contributed to an imperfect computer model, yet it returned a set of data we can analyze. In order to determine the mass of a black hole, I used Excel to produce an average of all of the mass data values. The final mass of the black hole was determined to equal 8.53 times 10 to the 33rd kilograms. Fnet was equal to 8.84527 times 10 to the 28th newtons. The Fnet in the parallel direction is 3.87584 times 10 to the 28th newtons, and Fnet in the perpendicular component is 1.10916 times 10 to the 29th newtons. So now back to the questions. So we're going to discuss how net force and its parallel and perpendicular components are different from the rate of change of momentum. So when we define momentum and force, they both do two different things. Think of momentum as what continues the motion of an object, and force is what causes the motion of an object. So net force's parallel and perpendicular components are what causes motion in a certain direction. They have a direct relationship, however, as Newton's second law states that Fnet equals dp over dt. However, they are different in the sense that the net force components are what causes the motion, yet the parallel and perpendicular components of momentum is what continues the motion. So imagine the black hole whose mass you found was removed and a different black hole was placed in the same location. If the observed star remains changed, then we would not be able to find a difference. So because our data is solely based off the motion of the star, then with no changes in that motion, our model would return the same values as the original black hole. It would be impossible to tell if the masses are different unless there is some change in the motion that we can factor into our calculations.